Okay, so I see your slide deck, but I see it in presenter view as opposed to the, yeah.
Cool. Great. Yeah, then we'll give it a few more minutes for other people to hop on, and then I'll have my colleague Gabby give some introductory remarks, and then I'll pass the screen sharing back to you.
Okay, thank you. Where are you located today? Are you working from the main office or from home?
No, so yeah, we're all remotely working now. We're part of the non-essential government staff, so we're kind of following the orders of Governor Baker. How about you?
Yeah, I've got 2 desks and basically a pretty open space here. So, you know, I'm here when I'm here, and then when I'm not, I'm at home.
Nice.
Yeah. Yeah.
So you're mostly able to continue working on the project and stuff?
Yeah, for the most part. I think the only real slowdown has just been you know, vendors slowing down while they try and figure out their supply chain, things like that. Yeah, normal stuff.
Yeah. Yeah.
But for the most part, since it's a small team, we have the ability to keep moving forward.
Good to hear.
My phone on silent. Do not disturb. It's a good idea. Okay. Do you know about how many people are registered to attend?
I'm not sure at the moment, but I think I can get that information to you after the presentation. And also, if you're all right, we may post this to our YouTube channel.
Oh yeah, no, that's fine. Yeah, I guess it's always helpful to know more. The more I know about the audience, the better able I'll be to communicate the excitement and the ideas and the technology. And I guess I'm sort of some general idea that it's a broad spectrum of some technical people all the way to some business-minded people or investment-minded people. So I've tried to tailor the slide deck to the diversity of the audience.
Got it, yeah. All right, so it's about noon. Gabby, if you want to kick it off, go right ahead.
Yeah, absolutely. So hi all, thank you for joining us virtually for a MassCEC CleanTech Spotlight webinar series presentation. To briefly cover some housekeeping items, all attendees are currently in listen-only mode. We'll start by quickly introducing the webinar series, and then we'll introduce the guest speaker for today's webinar and let them present on their company and technology. Following the presentation, there will be roughly 15 minutes reserved for questions from the audience. If you have a question, please use the question submission feature and type it in as the presentation is happening, and I can ask them on your behalf. Now, to give a short introduction to MassCEC's work, MassCEC's Tech Dev Program Suite consists of 3 different grant programs: Catalyst, Amplify, and Innovate. Each of these programs target providing support to clean tech startups and researchers at different points in their technical and commercial development, from prototyping to demonstration with industrial partners. Today's presentation is a Catalyst grantee. Jeffy Silverberg, PhD and CEO of Multiscale Systems, will present on the latest progress of his company. The stronger and lighter manufacturing materials Multiscale's technology is developing is making great advancements in the manufacturing industry. Thank you again for joining us, and please enjoy the presentation.
Okay, hello. I guess first things first, is there any indication that people can hear me and can see my slides?
Yep, both are working great.
Awesome, okay. So, I guess good afternoon, everyone. My name is Jesse Silverberg. I'm PhD in physics, a CEO and research director at Multiscale Systems, where we are making advanced materials that are lighter, stronger, smarter, and better. We are actually, yesterday, we celebrated our 2nd birthday. And so today in this talk, given the audience, I thought what would be fun to do is to give a sort of pop-sci introduction to the science and technology behind what it is that we're doing, and then let that segue into a bit of the business side of things in terms of how we're driving the technology into high-impact clean energy technologies. What I'm showing you here on the first slide are some examples of some of the things that we've been producing, and I'll have more to say about that as we get further ahead. But just to begin, give you this idea of where we're going with this. So we design and manufacture advanced structured materials. And conceptually, there's a pretty simple schematic here that you can take a conventional material, a plastic, a metal, a elastomer, you name it, and then you can combine that with a geometric pattern. And the combination of that is what is called a metamaterial. We specifically design mechanical metamaterials, and on the right here, I'm showing you some photograph of some of the things that we've done. These mechanical metamaterials are fabricated from polyurethanes, compostable plastics, carbon fiber reinforced nylon. We have examples that we've made out of stainless steel, aluminum, and copper. And so in each case, we've been able to vary the conventional material that we start with. We augment and design and engineer and optimize the geometric pattern. And then after we've transferred that pattern into it, we end up with the functional metamaterial. So it is, in a nutshell, what it is that we do. But that said, mechanical metamaterials, that's a term of art that not many people are familiar with. So you might ask the question, well, what are they? I mean, what are they good for, but what are they? And if you just type that into your search bar and look at images, you might see something that looks like this. If you stare at this for a while, you might come up with the impression that metamaterials are colorful, that they're geometric, and that they look like kind of like they're fun to play with. Like you see some things here, it's like, wow, actually, I kind of want to just squeeze that in my hands and see what it does. It looks like it's going to be interesting. To give you a bit more of a clearer picture of what this means, so what are metamaterials? They're a class of materials designed with a wide range of exotic responses to external forces. The reason why we're interested in these is they're often lighter and have fewer moving parts than an equivalent machine, and they can exhibit multifunctionality without a battery. So how we make these things is basically by building and modularly assembling smaller units where we use geometry to control mechanical function, and that was the slide I just showed you. And then more concretely, how do we do this? It's with the mathematics of origami. So I've learned that when I tell people this, I say origami, people often think of this picture, the traditional origami crane. Probably you might have seen this, or maybe even you learned how to fold this when you were in grade school. I'll just say that contemporary origami is actually pretty sophisticated. This is an origami sculpture of a snake wrapped around a scorpion. It's folded from one piece of paper with no cutting, gluing, ripping, tearing. You can see that it's one piece. One side of the sheet is brown, the other side of the sheet is green. And you can see that the artist was actually able to flip the orientation of the sheet to get the two-tone effect. Origami art like this is actually possible today because in the 80s and 90s, a group of mathematicians, computer scientists, and physicists took an interest in the mathematics of origami and developed tools to be able to enhance the design of that. That community also helped lay down the foundations and the tools for being able to start to probe how origami can be used to control the mechanical function of folded sheets. So for us, when we do mechanical metamaterials and we're thinking origami, we don't think about this. We think about something simpler and maybe a little less appealing to the eye. It looks like this. So this, let's see if this movie will play. This unit is called a square twist. And what you can see happening here as I squeeze this thing between my fingers is it has this nice mechanical popping or snapping action that goes back and forth. And this is a really nice entry point into the world of origami as a mathematical object and a material, a building block for materials, because this little simple design is incredibly rich with technical insights. So let's see here. We can take that physical paper and we can write it down on a sheet where I've now drawn here the outline in black, and then I'm using red and blue lines to indicate what direction the folds are going. This particular design can be parameterized with a couple variables. So for example, here a length, an angle phi, and then you can talk about what condition it's in or what state it's in by talking about the distance between the two gold stars, delta. Take a unit like this and we say, all right, here is a geometric design that's been parameterized. And as we vary a parameter, in this case, the angle phi, from one value that's low, like 20 degrees, you see is that popping action is actually quite weak as you go towards lower values of phi. If you increase the values of phi to something large like 70, all of a sudden, not only do you have a large popping, but now the thing crashes into itself. And so right off the bat here, what you can start to see is that geometry really has this overwhelming influence on what the mechanical properties of this really simple structure ends up being. Mathematically, there's a really bizarre mystery that shows up as soon as you start to try and analyze this, and it turns out that mathematically this thing is impossible, that it shouldn't exist. So I've written down a formula here. I don't expect that it'll mean a lot, but basically it comes down to this. You can calculate what this square twist should be as you vary one of the parameters. That same angle that I just showed you as varying, that's what I'm playing with here on the x-axis. And then I showed you here that opening and closing action, that's what I'm showing you here on the y-axis. And essentially what this equation says is that a square twist can only be on one of these black lines, the upper one or the lower one. But when we go and make these and start playing with them by hand and then make measurements, we find a real physical square twist sits on the red data points in this red band. And you can see that there is some agreement and that the trends do kind of seem to follow one another, but there's obviously some kind of disagreement. And that this disagreement has to do with the fact that mathematically, this thing should not exist. The reason is that geometry of a crease pattern isn't the only thing that matters if you care about origami. Specifically, let me pause this video. You can play it again. So here you can see that square twist. I paused it, and you can see that right here, there's the paper is bending. And bending paper does not show up in the geometry of the folding pattern, but it does show up as a property of the paper. And so when you start to see that somehow geometry does control the mechanics, but somehow the underlying properties of the material that we use to make the square twist do seem to surface, you can start to see how that interaction can now become something to play with. So we take this observation, we go into the lab, we start making measurements. This is just a simple instrument that we built to be able to tug on this square twist in a controlled fashion. I've slowed down the video so you can see the pop as it happens. We're making the measurement on one side, we're controlling the displacement on the other. The schematic on the left just gives you an idea that this is a force displacement measurement, very typical, very basic type of measurement you would do if you want to state the mechanics of a structure. And then you get curves that look like this, where here I'm showing you a force displacement relationship. And the red curve is this big snapping action that you get in one of them. And the blue curve is that really weak, flimsy, no snapping action that you get in another. And this really just ends up being the tip of the iceberg in terms of the measurements that you want to make. What comes out of these measurements, though, is a hypothesis, and that hypothesis then leads you to a prediction. And that prediction is that if I could make an origami that folded and unfolded itself, meaning I didn't have to tug on it, if it could just fold itself, then I know what the force displacement relationship should look like. So it's a weird hypothesis to make, but there's reasons why it's the right one to formulate. And then you say, well, how do I make an origami square twist that folds and unfolds itself? That seems like such a bizarre and archaic thing to do. It turns out it's doable. And one way to do it is with polymer gels that swell. And by making this sort of sandwich structure where you have a blue layer of a gel and then an orange layer of a gel and another blue layer of gel, and then giving each one of these gels different swelling properties and then patterning on the top and the bottom different geometries, right? Like this ends up being a convoluted chemical engineering process, but it works. It works, and you can make a self-folding origami structure. Now, if you notice the scale bar here, it says 200 microns. This self-folding origami is sub-millimeter in size, that from edge to edge, we're looking at about half a millimeter. So the tip of a ballpoint pen is the size of this origami structure. What I'm showing you here is that we took those self-folding structures with different angles, just like the paper ones I showed you on the previous slides. We put them on a microscope and we did three-dimensional imaging of them just to make sure that these microscopic structures were doing what we think they should be doing. And then we did the measurements. So I don't want to spend a lot of time going on what the specifics of this are, but essentially in this experiment, instead of pulling on it with a force, we heat it up, and the heating gives this curve, this red band, that as you heat it up and up and up, it stays kind of folded and folded and folded, and then it hits a critical temperature and pop, the thing unfolds. Then we cool it down, and as it cools down, 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 snap, it folds back up. We can vary the angle just like we did before, and we can change the amount of that popping action, the size of that loop. And we can put all the data together. And what matters here, what matters is that our hypothesis ends up being confirmed. That yes, in fact, we do understand the interplay between the geometry that we've embedded in the material and the properties of the material itself. And when you sit back and you stare at a blank wall for the better part of a day, what you realize, the lesson that comes out of this is that size doesn't matter. That if you're going to use geometry to make mechanical metamaterials, you can make them microscopically small, or you can make them as big as a solar panel on a space station. And at the end of the day, geometry does not care. It does not care. That as you go up and down in scale, you can engineer the metamaterial properties independent of what size of the structure you're working on. So that ends up being important because it's not sufficient to just do one structure. At the end of the day, you want to start doing tessellations, because tessellations give you sheets, and sheets become the building blocks of other structures, other materials. So here what I'm showing you in this video is a pattern. This pattern is called the Mura-Ori. It was invented by a Japanese astrophysicist who was also an origami artist. And he invented this pattern as a way to compactly fold up solar panels to put them up into space for satellites. The pattern itself is inspired by patterns that we see in nature on leaves, or in this case, embryonic villi, which is just a nice way to say the inside of your intestines as you are going through development. So this microscopic image here is actually the inside of an embryonic intestines. But nevertheless, I mean, again, that pattern shows up everywhere. And again, geometry doesn't care about size. And so if you start to think about these patterns, again, as a material, and again, we come back to this idea of writing down angles and lengths, and then we think about red and blue lines here as being the direction of the creases. You can parameterize a crease pattern. You can then start to fold these structures. Here I'm showing you a three-dimensional image of one of these samples that we made in a lab. And the overall three-dimensional structure is given by the angle alpha and the lengths L. And as we vary those angles and lengths, we can actually tune the properties of this structure. One of the really surprising things that comes out of this is that you can make one of these patterns, fabricate the sample, and then you can start to actually modify or augment its properties even after it's been created. So here what I've done is I popped one of the units, I've inverted it, and now when I try to squeeze it, you see that it does not collapse all the way anymore. So by introducing one of those, what we call pop-through defects or PTDs, that allows us to enhance the stiffness of this material as if it was a sort of mechanical pixel. Not only that, the introduction of these mechanical pixels is reversible. So you can add them and you can remove them. And I'll say this is pretty much the last technical slide before I start segueing. But what it comes down to is this, that you can come up with a bunch of different configurations for how you introduce these reversible deformations. And then you can say, all right, I want to rationally program the stiffness of this material. That's the black lines in this chart here. And now I can go through, in this case, 40 testing cycles where each time I want to program what the stiffness is, and I'm going to measure it just to make sure this does what I think it should do. And that's the red data points. And what you're seeing here is that even though we've fabricated this structure once, we're able to rationally dictate what its physical and material properties are going to be. So this basically ends up being sort of a capstone of when we go from exploratory science to rational design. And each one of these images here, each one of them could be a 45-minute technical talk to an academic audience. But needless to say, we started off doing exploratory science, trying to understand this connection between geometry and mechanics. It led us to the point where we turned around and said, well, okay, we understand how to go forward in terms of make something and measure its properties. But what if we wanted something with a specific set of properties? How do we design that? And so that's the lower section of images here. We started exploring those questions where we moved into rational design. We've been successful in there, and we've now gotten to the point where we can do computationally generated structured materials. These structures are three-dimensional. They're no longer just bare origami. There's a lot more technical sophistication that goes into the design, the validation, the fabrication of things like this. But when I say these are mechanical metamaterials inspired by origami, I hope you can think all the way back to the origami crane at the roots of origami and just these basic individual units and poking and prodding them to understand how the crease pattern, how the geometry starts to affect the physical properties. And it's basically that game. It's that game of using geometry and playing with geometry that allows us to create these various product lines. So this is where I started the technical portion. I'm going to end the technical portion here. I said again, we design and manufacture advanced structured materials. Conventional materials, I've showed you thin sheets like mylar or paper. I've showed you self-folding polymer gels. On the right, I've shown you polyurethanes, carbon fiber reinforced plastics. We've got metals. All of those are conventional materials that are out there that are already mass-produced and widely available. Our value add, the way that we're able to introduce new and desirable properties into materials is through that geometric pattern. So using that origami-inspired design that has led us to all the engineering expertise and know-hows, it allows us to get to that functional metamaterial. What does a functional metamaterial look like? What is the real need here? What does this end up being? Well, I want to turn your attention now to a problem in the transportation sector. And I think this is where we start to interface more concretely with the MassCEC community, where we care about issues related to greenhouse gas emissions and harm reduction coming out of, for example, the transportation sector. In the US, the transportation sector is something like an $800, maybe $900 billion market. It produces a couple billion metric tons of CO2 per year. And a lot of that CO2 production is coming out of vehicles such as semi-trailers. Semi-trailers, of course, are responsible for moving the goods and products that we consume, everything from the grocery store to the laptops that we're all sitting in front of, to the Amazon deliveries that have become part of our way of life in the quarantine era that we're in. About 30-ish years ago, these semi-trailers, these box trailers, like the picture I'm showing you here, those were manufactured from sheet and post. It was basically a giant wooden box on wheels. About 30 years ago, a new material came onto the market. It was a high-density polyethylene composite panel, a sandwich panel, if you will. I'm showing you on the left here a schematic. Is basically a stainless steel skin, outer layers wrapping this high-density polyethylene foam. And that was introduced as a lightweight composite panel. Our version of this is about, let's say our metamaterials compared to these composite panels offer substantial amounts of weight reduction. In particular, these quote-unquote lightweight composite panels are about 4 to 5x heavier than our metamaterials. And so even though we can offer comparable strength and stability for the design and manufacturing, we basically have the opportunity here to introduce a new generation of lightweight materials into the construction of semi-trailers. Just to give you an idea of what that means in terms of the market, there's something like 250 to 300,000 new trailers manufactured every year. It's something like a $4 to $12 billion market opportunity, where even a 10% weight reduction on the semi-trailer leads to, about a 6 to 8% improvement in fuel economy. So for small fleet operators, we're talking about reduction of on the order of a couple hundred metric tons of CO2 per year, while at the same time increasing the profitability of the semi-trailer by about $1 million per year for small fleet owners who operate, say, something like 100 semi-trailers. What does this mean in terms of our market? Well, our beachhead market is the semi-trailer manufacturing. Again, 250 or so thousand new trailers per year. Those new trailers, 80% of them come from these 5 manufacturers: Wabash, Hyundai, Transled, Great Dane, Utility Stoughton. And they're all manufacturing semi-trailers with this same type of composite panel materials. We're in the process now of working with these companies to be able to identify what their pain points are and how we can transition our mechanical metamaterial as a lighter weight solution relative to the current high density polyethylene that they're using. If we can address the manufacturing concerns that have prevented other lightweight materials from being successful in the past, then we can provide better fuel savings, reduced emissions, and greater profitability for the people who buy the trailers from these manufacturers. This ends up being a great beachhead market for us because it allows us to prove out the scalability and the viability of this materials, as we can then go beyond our beachhead and start looking at electric vehicles and hybrid electric vehicle manufacturing. I've shown here the logos of a number of companies, many of which we all have seen on the roads around us. Right now, the electric and hybrid electric vehicle manufacturing market is something like $900 million a year domestically being spent on new cars. And so the weight reductions that we can provide would allow these electric vehicles to go further on a single charge, while at the same time being able to create a greater efficiency that is limiting the consumer adoption of electric vehicles. I'll say that we also have gotten some traction from the DoD. The Army in particular has taken an interest in this type of materials technology, as well as the Department of Energy. They also have taken an interest in what we're doing. And we're able to say today that we're receiving some great support from these government-funded, federally funded offices to help make this technology possible and to field it into the semi-trailer and eventually the automotive manufacturing industries. I'll just say, why are we going to win in 2 plots here? On the left, basically, we are those potato-shaped blobs. This is where I can say that we provide better performance. It's about 10x reductions in the mass density, 10x reductions in the weight without sacrificing the stiffness. On the right, the plot here basically says that we can do all this at an affordable price, that essentially we're starting with the same raw materials as anyone else has available, but our value add is a relatively low cost, that to design these mechanical metamaterials to achieve the performance benefits. That is a value-added manufacturing process that has relatively low costs. I'll also add that in incognito here, in stealth, I'm also indicating what our cost of goods sold and what our revenues are going to end up looking like, since our costs of manufacturing are essentially the same as any other manufacturer working with these types of materials and fueling them into industry. We can use those as good reference points for estimating what our cost of goods sold will be, so we know what our margins and revenues can look like. Again, I think I mentioned when we started off that we celebrated our 2-year birthday yesterday. Looking back at the traction and revenues that we've had, so far, we've basically had a stellar 2 years. We launched, we ended up getting our first few dollars through a DoD or an Army-sponsored competition. It was $5,000. It allowed us to buy our first piece of fabrication and testing equipment. From there into 2019, we had a great year with NSF and NASA sponsoring us through SBIR Phase 1s. Our NASA has now gone into a Phase 2 application. Our NSF is on that track and will be sent out soon. We joined the Mass Challenge Accelerator to basically learn about how to do a startup. Our approach to this is coming out of the technology, and we want to be a viable company. And so we entered into Mass Challenge as a way to try and get a boot camp on what it means to start a business. In 2020, we have been funded by MassCEC, sponsors of this event here. We received a DOE SBIR. We joined the Lever Accelerator. We are now in the X-Tech 4.0 competition, and all of this is leading to something like about $700,000 of equity-free revenues that have really fueled our R&D, our growth, and our capabilities. Looking ahead, we basically have a technology and a business roadmap. We're looking at getting our MVP developed and designed for large scalable manufacturing without loss of performance. We have QA/QC benchmarks to hit. We've got a 5,000-mile road test to do. Cost of goods pricing is all going to get detailed in as we nail down these manufacturing questions. And then sort of looking externally to the company, we have ongoing customer discovery interviews. We're building strategic partnerships. As we've talked with the semi-trailer manufacturing companies, they said, of course we've tried lightweight materials, and we took a lot of them out of the aerospace industry to start with, and it turns out that they weren't suitable for semi-trailer manufacturing. And it was those conversations, those customer discovery interviews, where we learned about some of the problems that existing lightweight materials have had in translating across industries, which has helped inform our technology development roadmap. Sort of looking ahead, really the major milestone here is a 100,000-mile road test. What we've learned is that a standard way of vetting materials before they go into mass production is that they build a demo trailer and they drive it for 100,000 miles. You can do the math on the back of an envelope, and what you see is that's basically driving a semi-trailer coast to coast, nonstop for a year. So we're looking at that as the major milestone, that if we can get through that road test and demonstrate success with our product, then we'll be ready to field into commercial sales. I keep saying we. Who are we? Well, I'm over there on the left. I'm Jesse. Art is my technical colleague. We did all of the basic R&D during our PhD and postdoctoral research at Cornell, Harvard, UMass Amherst, with a great set of colleagues and advisors. That was where the genesis of this work on origami really started. When we left academia to go and do this on the commercial side, we brought on Pat. He's a friend of 20 years. He's been with a small business for 10 years. He went from 10 employees to 50 to 100. They float seasonally. He's just, when it comes to making things happen, I don't know anyone better to have around to being able to operationalize a plan. We recently brought on Karen and Prajwal to help round out some of the needs in terms of personnel, and we feel like that we've built a really great team that are really going to help drive us forward moving into the next few years. Last but not least, I just want to highlight that as a company, we take evidence-based methods seriously, and they are baked into our DNA. All the way at our roots, where we're doing peer-reviewed research, to today, where we're using lean startup principles to guide our product development and our R&D efforts. That yes, we are currently an R&D firm, but we don't want to be doing R&D forever. We are on the journey to commercialization, and that's a journey that does require evidence-based methods to be successful. So I just want to say thank you to the agencies that have funded us, to the universities where we got trained, to the organizations that have helped us as a startup find our footing, including MassCEC, who again is helping to sponsor this event today. So with that, I think I'll close. I want to thank you for your time and attention. I'd be happy to take any questions you may have.
Yeah, thank you. This has been great. A reminder to all the attendees to please submit your questions in the question box, and I'll ask them on your behalf. To start it off, I was wondering how exactly the material is installed in the semi-trucks you were mentioning. Is it installed in retrofitting or new trucks? And is there a difference from your perspective in terms of potential impact or any specific value proposition for your company?
So our focus is in new semi-trailer construction. The reason being is that retrofitting for lightweighting panels is not a great market opportunity for that. On the other hand, if we can work with the manufacturers and get them in the semi-trailers up front, that ends up being a more commercially viable pathway forward. In terms of the technical of like how you do it, well, the answer is that the materials that are currently being used are these, like I say, foam that's a surprisingly heavy foam that's sandwiched between two stainless steel plates. If you look on the top right, what we have is actually the version of the technology called METACORE. And METACORE is the product line that we're aiming for here for semi-trailer construction. The interior of the metamaterial has a specific geometry that provides the necessary loading and the lightweighting features of the metamaterial. But you notice that it has already attached to it these flat facets, those faces, sort of, see there's in the blue patterns there. That's actually textured in order to allow the resins and epoxies that hold the stainless steel plates to the core material to provide great contact. Other material solutions from aerospace didn't have that, and as a result, there was delamination and a number of QA/QC issues. So we've designed METACORE to be able to be easily installed during the construction process.
Got it. Another question is regarding safety certifications. Are there any specific certifications necessary for the installment of the materials in semi-trucks or any of the other market use cases?
So before doing road tests, the semi-trailer manufacturers have internal R&D tests. They all have their own R&D facilities, actually. Those engineers are responsible for vetting any new materials and performing the tests that are required in order to assure that these materials will be used in a safe fashion. We've gotten basically lists of what those tests are. We have a good idea of what it is that we need to do and what we need to demonstrate in-house before we hand these materials off to them. But when we do, we will be confident that the materials will be safe to use and that their internal tests, we'll have a good idea of what their internal tests will say before they even know it, because we will have done them first.
Got it. And when you hand the materials off to them, would Multiscale control the manufacturing, or would you license that to the like construction entity of the entire vehicle?
So the semi-trailer manufacturers, what we've learned through our customer discovery interviews is that generally speaking, they would rather just buy them already made. They don't want to manufacture them themselves. So that means that we've got to come up with a scalable manufacturing process, either something that we do in-house or something that we can subcontract out to a manufacturing firm. And what that ends up looking like depends a lot on what manufacturing process we land on that's both scalable, as well as ensuring that we get the QA/QC that we need. So this is where we go through that sort of MVP 1.0 product development, design for manufacturing virtuous cycle of design, fabricate, test, design, fabricate, test, design, fabricate, test. And as that process iterates, it will inform us of what is the most viable manufacturing method to move forward on, which will in turn inform us on whether we're manufacturing these in-house or whether we're subcontracting the manufacturing to a third party.
Got it. And then kind of going back to your commercialization plan, what are you hoping to gain from the second accelerator program you're participating in?
So the first accelerator we went into, Mass Challenge, was helpful because we did not have any startup experience. Well, I'll speak for myself. I definitely did not, and I was new to this environment. So that was a really good opportunity to just become exposed to the world of startups and accelerators and what's available and what's possible. The second accelerator that we've entered, Lever, through their Berkshire Sustainability Challenge, this for us has been really helpful because it's a bit more of a bespoke program. It's a smaller cohort. There's a lot of interaction that has more tailored one-on-one focus for us as a company, but for the clean energy focus of the challenge sponsored by the accelerator. So I think for us, having gone through Mass Challenge first to see the spectrum of what's out there, it was more of a almost like a buffet. And then now to go into Lever, I think we have a better idea of what it is that we need, and as opposed to if we had not been in a program like that otherwise.
Great, thank you. Another thing our team was hoping to get an update on was the Catalyst project you're participating in at the moment.
Yep.
Where are you at in that project right now?
So yesterday, I just finished up a fabrication round of 100 MetaCore panels. I stacked them all on the desk, and they actually make this complete arc. Like you hold it up, and it's like, wow, it's just this giant mass. And so the next step is to go and start performing destructive testing. A big portion of what it is that we're hoping to do, or that we're aiming to do with the Catalyst program, is to scale up manufacturing of the prototypes to be able to more quickly iterate and converge on the final design. I mean, with the print, so with the infusion of cash that we got from the Catalyst, we're able to increase our prototyping capabilities, I guess, 6-fold. So instead of producing 1 or 2 at a time, we're now producing 12 at a time. And that is basically addressed a major bottleneck to progress that we were wrestling with before receiving this grant.
Great to hear. And then if you wouldn't mind going back to the slide you had with all the different entities that you've had kind of strategic conversations with. And if you could maybe talk about in a bit more detail the conversations you've had with these entities and like what specific other beachhead markets you're looking at for this technology.
So the conversations that we've had most extensively have been in the semi-trailer manufacturing. sector. We made a pretty early on decision that we did not want to use electric vehicles or hybrid electric vehicles as our beachhead market, just because of the nature of the market being relatively fractured and the technology itself still being developed. We wanted to do something that was a bit more mature and a bit riper for disruption. So the in-depth conversations have been really at the top of this slide. Wabash, Hyundai Transled, Stoughton, Great Dane Utility. And what we've learned in these companies is that there is a pretty clear distinction in terms of who holds the technical decision-making power, who holds the financial decision-making power, and what it is really that they're looking for when they vet new materials. The fact that we're able to offer something that is lighter than what they're currently using, yes, that does address the main overriding focus, what it is that they're looking to accomplish when they engineer the next generation of semi-trailers. But the reality is that in those conversations, we've sussed out a whole spectrum, a whole set of other hosts of challenges that prevented other solutions from being successful in the past. So everything from repairability, like what happens when you repair, like when the material gets a hole, how do you fix it? To, I've mentioned this before, QA, QC issues that have shown up in some of the materials used in aerospace. Costs end up being a big issue, of course. The availability at scale. You can do a really interesting back of the envelope calculation that if you take the number of new trailers manufactured per year, estimate the amount of square foot of paneling that's used in that 1 year of production, what you find is that the foam material that they're using in the interior right now of the semi-trailers, that foam is being produced and consumed at a rate of about 9 square feet per second, every second of the year, in order to meet the demand for this industry. And so when you look at that number, it really puts into perspective what kind of manufacturing challenges that have to be met. But that was all information that came through these customer discovery interviews and conversations.
Great, thank you. I think those are all the questions we have for today. Thank you again for presenting. This was super interesting, and we're definitely excited to see what comes out of this Catalyst project.
Well, thank you very much for providing the support and the opportunity today to present to the audience. I think probably the last thing that I'll mention is that I think I already said that we've already been strongly supported by Phase 1 SBIRs from NSF, NASA, and the Department of Energy. And as we go into our Phase 2 preparation, I'll say that I know a number of these federal agencies do have matching or matching options. And so if there are investors in the community who are listening to this talk and they have interest in providing or having a conversation about matching funds to these zero equity grants, I would love to get in touch to talk to you a little bit more about in depth what our technology and our commercial plans are really looking like, and to have those conversations to see if there's some opportunities to work together.
Great, yeah. And then also, I'm not sure if you're familiar, but just a quick plug for MassCEC's Amplify Mass program. The program does provide cost share to federal research grants to clean energy research groups and startups. And that program is on our website. I can also follow up with email if you're interested.
Awesome.
Yeah, so thank you again. Have a great weekend.
Great, thank you too. Stay well, stay safe.